Welcome to AudioCert, where the official study guides are brought to life. Today, we're embarking on a deep dive into an absolutely essential area for anyone serious about cybersecurity and digital forensics. We're looking at the EC Council Computer Hacking Forensic Investigator, the CHFI certification, specifically the 3.12.49 version. Now, this certification, it isn't just about understanding how computers work at a surface level. No, not at all. It's really about equipping professionals to meticulously analyze digital evidence, to piece together sequences of events from, the smallest fragments of data, and ultimately to combat the ever-evolving landscape of cybercrime. In a world where every piece of data, maybe a corporate email or even a deleted file, can be a crucial clue, well, forensic investigators are truly the unsung heroes of the digital realm. Their role is critical, ensuring justice and security. And the stakes in their investigations, they're incredibly high, touching everything from corporate espionage to complex criminal cases.
And, to excel in that critical, high-stakes role, a truly solid foundation is paramount. Absolutely essential. That's exactly why we're dedicating this deep dive to Chapter 5, Windows, Linux, and Macintosh boot processes. Now, for some, the term boot process might sound a bit, dry, maybe technical jargon just when the computer turns on, right? And yeah, it is that, but understanding how a computer systematically comes to life from a completely inert state is absolutely vital for any investigator. Think of it this way, imagine someone waking up every single day with complete amnesia. They wouldn't just spontaneously know everything. They'd have to rediscover who they are, where they are, how to function step by tiny step. A computer does something remarkably similar every time you press that power button. It starts as a blank slate, devoid of memory or instructions. And through a series of tiny, sequential, yet incredibly complex steps, it builds itself into a fully operational system. For a computer hacking forensic investigator, this rediscovery process is precisely where crucial clues can be found. Clues about a system's state, maybe potential tampering, or even hidden malware. And these clues often manifest before the operating system fully loads and potentially covers its tracks. This makes this early stage a goldmine for initial forensic analysis. So throughout this deep dive, we'll meticulously trace these fundamental step-by-step actions that a computer takes, building from inert hardware to a dynamic, interactive system. And we'll explore how these processes unfold across the major operating systems, Windows, Linux, and of course Macintosh.
Okay, let's unpack this then. The term boot itself, it has such a classic, almost historical feel to it, doesn't it? Kind of evocative of a bygone era in computing. Where does that even come from, and why is it still so fundamental to how we talk about computers starting up?
Yeah, that's an excellent place to start, and it really is part of computer lore and history. It's kind of neat, actually. The term boot actually comes from an older, more folksy phrase, pulling oneself up by the bootstraps. Or maybe more simply, just from the bootstrap itself, those little leather tabs on boots you use to pull them on. In computing, it implies a self-starting, self-sustaining mechanism where a system can initiate itself and load its core components with minimal external help. It's really a perfect metaphor for computers' journey from off to on. And it's truly fundamental because despite the vast differences in operating systems and hardware out there, almost all modern systems capable of running Microsoft or Linux or even macOS share a remarkably similar initial boot-up process. It's this universal, foundational sequence of very small, almost atomic programs, executed in a precise order, each building upon the last until the entire operating system is loaded and operational. Understanding the shared foundation is really crucial before we dive into the OS-specific stuff.
Right? So it's not just flipping a switch. It's this whole carefully choreographed dance of tiny, intricate steps, like a machine slowly coming to life, piece by piece. Where does that intricate dance of awakening begin? Like right at the very, very beginning.
It begins with the most basic, the most essential step, applying power. Simple as that. When you flick that power switch or press the button, the internal circuits in the power supply unit, they go through an initial surge. This is a critical moment where raw electrical energy is converted and stabilized. After that initial jolt, these circuits settle into a smooth, stable output of direct current, typically at precise voltage levels like 5 volts and 12 volts, which are vital for all the internal components. Once these voltage and amperage levels are within their specified safe operating parameters, meaning the power is clean and reliable, a crucial signal is generated. This is known as the power good signal, and it's immediately sent to the computer's central processing unit, the microprocessor. You can really think of this as the computer's actual wake-up call after that initial shock of electricity. It's the system basically saying, all right, I've got stable power systems are nominal, I'm ready to begin my internal diagnostics.
The power good signal. It sounds like the computer's first conscious thought. Almost like, okay, I'm awake now. And once it gets that signal, that green light of stable power, was the very first thing the microprocessor does with it.
Indeed, it's like the computer's first internal nod. Yep, got power.
Yeah.
Upon receiving that essential power good signal, the microprocessor immediately goes through a reset. And this isn't just a casual restart, it's a deep foundational clearing process. All its internal registers and any residual memory are cleared out, which effectively puts the CPU into a known, clean, predictable state. This ensures that no previous operations or, corrupted data can interfere with the critical startup sequence. Once it's reset, the microprocessor begins executing a hard-coded program. This program is stored in what's called read-only memory, or ROM. Specifically, it's within the basic input-output system, which we usually just call the BIOS. And this execution starts at a very specific, predefined memory address, hexadecimal F00, that's HF00. This small, foundational program is designed to perform a series of initial self-tests. It checks the basic motherboard functions and attached hardware. This entire sequence is what we call the power on self-test, or POST.
The POST, right? That's a term I've definitely heard before. Usually when a computer isn't starting up right, and maybe there are some alarming beeps happening, how does the computer communicate problems during this really early stage, especially before anything visual even appears on the screen?
Yeah, that's what's absolutely fascinating here, how it communicates so early on, often before the display is even fully active. Traditionally, if an error happens during POS, the system reports it with a series of distinct audio beep codes. These beep patterns, they aren't random. They're standardized, or at least common, to specific BIOS manufacturers. And each pattern can tell you pretty much exactly what's wrong, maybe a memory issue, a graphics card problem, a CPU error, something like that. Now, for an investigator, decoding these beep patterns is actually crucial. It can immediately pinpoint a hardware-level failure, which might indicate intentional tampering, component swapping, or even just physical damage. But beyond those beeps, most modern computers also send a diagnostic code to an internal port, usually port H80. And this is a potential goldmine for forensics. Imagine an attacker physically tampering with the system, maybe swapping out a legitimate component for a malicious one, or even trying to remove key hardware. These diagnostic codes, you can often read them with specialized diagnostic cards that plug into motherboard slots, ISA, PCI, AGP slots. They could reveal an unusual sequence or an unexpected error that points directly to hardware-level tampering before any software detection can even load. Understanding these codes is like having a direct line into the computer's earliest health report, which can be invaluable when you're trying to reconstruct a hardware-level compromise. It's worth noting, too, while H80 is common, some vendors use other ports. Like ASUS systems might use port H30 for their diagnostics.
Okay, so it checks the core functions and can signal issues with beeps and these diagnostic codes. Makes sense. But eventually we expect to see something on the screen. What happens next with the display?
Exactly. After these fundamental internal checks, the very next critical step is for the BIOS to actively search for and initialize a video display adapter. The video card itself has its own read-only memory, its own ROM. Once the BIOS finds a video card, it verifies the checksum of that video ROM, basically making sure its integrity is good, that the code hasn't been corrupted or, crucially, maliciously altered. After a successful verification, the BIOS executes the video ROM code, and that brings the display adapter to life, allowing it to send signals to the monitor. The visual outcome can range, from a simple blinking cursor appearing on the screen.
Yeah, the classic sign.
Right, that classic DOS-era sign of life. Or in many modern systems, you see those flashy, often colorful manufacturer logos we've all come to associate with our computers starting up. This is the computer's way of saying, okay, I can finally see now. I can communicate visually.
That makes perfect sense. Now, you mentioned earlier there's a difference between starting a computer for the very first time or after a full shutdown versus just restarting it. How does the POST process handle that distinction? Warm versus a cold start, isn't it?
It does, yeah, and the BIOS is quite smart about differentiating between those scenarios. It performs a quick check at a specific memory location, H0472. It's looking for the hexadecimal value H1234. If it finds H1234 there, that's an indicator of a warm start, meaning the computer is being restarted from an already powered-on state, maybe after a crash or a user reboot. Any other value at that location signals a cold start, where the computer is coming up from being completely powered off. Now, if it's a cold start, the computer performs a complete and thorough BIOS post. It checks everything. If it's a warm start, an abbreviated post is typically done. In many modern computers, your BIOS settings actually let you skip certain time-consuming checks, like a full memory test if you're just restarting. Saves a few seconds. For an investigator, this distinction can be pretty important. A warm start might bypass certain low-level checks that maybe a bootkit or other persistent malware relies on. Conversely, an attacker might force a cold start to ensure their malicious code loads fresh. Or they might try to manipulate this check somehow to evade detection. So understanding this behavior helps us predict potential attack vectors or manipulation attempts.
That's a clever optimization, but also, like you said, a potential avenue for manipulation. Interesting. And speaking of memory, what kind of test does it run on the random access memory, the RAM, if it is a cold start? I imagine that's a critical component to check thoroughly.
Oh, absolutely critical, because RAM is where the operating system and all your running programs actually live. So if it's a cold start, the computer performs a rigorous RAM test. It systematically reads and writes to every single memory location in the random access memory. This isn't just a quick scan, it's an exhaustive verification. It makes sure every bit of that temporary storage is working properly and reliably. This check is vital because the entire OS will soon rely on RAM for everything it does. Even a single faulty memory cell could lead to system instability or data corruption. On most systems, you'll actually see a counter or maybe a progress bar on the screen during the stage, showing you the status of this memory test as it goes through, megabyte after megabyte of RAM. From a forensic standpoint, a failing RAM test during post could indicate hardware degradation, sure, but also in rare cases, physically tampered memory modules or even sophisticated hardware implants. Such an error would likely be recorded in those diagnostic logs we talked about, providing an early alert to an investigator.
Okay, so it's meticulously checking all its internal components before moving on. Makes sense. What about the peripherals we interact with, like the keyboard and the storage drives? Do they get a chance to introduce themselves during this process?
They absolutely do. As PST nears the end of its basic hardware checks, it shifts attention to the primary input device, the keyboard. It doesn't just check if a keyboard is connected, it actively polls for any key presses. So if you've been impatiently tapping, say, the DEL key to get into the BIOS setup menu, or maybe F12 for a network boot, that information is stored in a temporary buffer for action once the PS process finishes.
Oh, okay.
Now, for an investigator, this little detail can be surprisingly revealing. Imagine a scenario where a user might have been frantically pressing F8 trying to get into safe mode, or DEL to enter BIOS setup, but the system shows no record of these attempts when analyzed later. This could indicate a keyboard failure, yeah, but maybe, more sinisterly, a system designed to ignore specific input to prevent recovery or intervention. Immediately after the keyboard check, the computer probes for the existence of any floppy drives if you still have one, or hard disk drives, and then any other storage devices. Any devices it finds are then compared to the configuration information stored in the CMOS memory chip on the motherboard.
Right, the battery-backed one.
Exactly. That special non-volatile chip that retains basic system settings like date, time, boot order, even when the computer's off, thanks to that little battery. It's how your computer remembers its basic setup. For forensics, the CMOS settings are a potential treasure trove. An investigator would definitely examine these settings. Has the boot order been altered to load from, say, a hidden USB drive? Have BIOS passwords been set or removed? These could indicate unauthorized access or attempts to hide things.
That CMOS chip is so crucial then for maintaining those persistent settings, almost like the computer's long-term memory for its fundamental configuration. What about other specialized adapter cards? Things like sound cards, network cards, maybe RAID controllers. Do they get a chance to chime in during post?
They absolutely do. They act as crucial extensions to the motherboard's core capabilities. The BIOS then systematically scans designated memory ranges, typically from hex C800, HC800, up to hex DF80, HDF80. It's specifically looking for other ROMs, read-only memory chips, located on these various adapter cards. Sound cards, network cards, dedicated RAID controllers, like you said. These ROMs contain additional code that needs to be executed to properly initialize those specific devices. If an adapter card ROM is found, its checksum is thoroughly tested first, again to ensure its integrity, making sure it hasn't been corrupted or critically tampered with.
Always checking.
Always checking. Only after a successful checksum verification are the programs found within that ROM executed, bringing each respective device online. Now, for an investigator, this is a prime area to look for sophisticated malware or even hardware-level implants. Think about a malicious network card with its own altered ROM. It could potentially hijack network traffic or exfiltrate data at a level way below the operating system. Very stealthy. Also, if new devices are detected during this stage that weren't previously configured, the system might even display the BIOS setup screen automatically. giving the user the chance to make those modifications permanent in the CMO settings. That interaction point itself could be significant for an investigator to observe.
It really is like a grand unveiling of all the hardware then, each component announcing its presence and readiness. And what's the final, universally recognized sign that everything went okay, that the computer has successfully completed its self-checks and is ready for the next big step, loading an operating system?
Traditionally, the successful completion of the entire power-on self-test is signaled by a single, distinct, and usually quite reassuring beep.
The single beep.
That single beep, it's the computer's way of saying all clear. It tells you, the user, and more importantly, the system itself, that all the basic hardware checks have passed. Every critical component has been initialized and verified, and the computer is now in a stable state. It's primed and ready to proceed with the next major phase of its awakening, locating and loading the operating system. No news, or rather, just that one single beep, is indeed good news in this case.
So it's this very disciplined, step-by-step diagnostic process, making sure the hardware foundation is solid before anything else happens. But what truly stands out to you here for a forensic investigator? Where would they be looking for the most critical clues or anomalies during this whole POST phase?
Yeah, what's absolutely fascinating, I think, is that even before the actual operating system loads, these initial checks and processes can reveal really profound hardware issues. Or, maybe more importantly for us, even insidious attempts to bypass normal boot processes if we're looking for anomalies. If we connect this to the bigger picture, knowing these tiny sequential steps helps us understand precisely where a system could be tampered with at the lowest possible level. For instance, modified BIOS firmware itself, that's a big one. Or maybe a diagnostic card reporting unusual post errors, or an unexpected sequence of initialized devices. These could be crucial. This isn't just about a computer failing to start. It could indicate a hardware-level compromise, where an attacker has actually altered the foundational instructions of the machine itself. An investigator needs to be acutely aware of what a normal post sequence looks like for a given system, including the expected beep codes, the diagnostic outputs, the initialization order, all of it, so that any deviation, even the smallest hiccup, stands out immediately as a potential indicator of compromise. This early-stage forensic analysis can be vital in uncovering things like rootkits or other low-level threats that load before any software-based security measures are even active.
All right, getting in before the guards are even awake.
Okay.
So once the computer passes its self-check, gives that reassuring beep having established its hardware health, its next critical mission is finding an operating system to actually start doing something useful. And that's where the master boot record, the MBR, comes in, right? It's essentially the OS dispatcher for traditional systems.
Precisely. After a successful post, the BIOS has done its initial hardware inventory and health check. Its job isn't over, though. Its next task is to locate an operating system. To do this, it systematically searches for something called a volume boot sector. Its traditional, universally recognized location is at cylinder 0, head 0, sector 1 of the default boot drive. Now, historically, the default boot drive was often the first floppy disk drive. Seems ancient now.
Definitely.
But modern BIOS configurations are much more flexible. You can designate pretty much any bootable storage device: an internal hard drive, an external USB thumb drive, an optical disk, even a network interface card. The BIOS simply follows this configured boot order until it finds a valid boot sector somewhere.
And what happens if, after all those checks, it just can't find anything bootable? Not in that crucial first sector or anywhere else it's configured to look. What kind of signs would an investigator see then?
Well, if the BIOS doesn't find any bootable code at that first designated sector, it'll then look for a master partition record at the same location. If neither valid bootable code nor a master partition record is found, the system will typically display those common error messages that many of us have probably seen at some point.
Oh, yeah.
Things like non-system disk or disk error, replace and strike any key when ready. Or maybe disk boot failure, insert system disk and press enter. Now, for an investigator, these messages aren't just frustrating user alerts, they are crucial clues. They immediately indicate a missing, corrupt, or potentially maliciously overwritten boot sector, or MBR. This could be due to a failed drive, sure, but it could also be a deliberate act of sabotage or a severe malware infection rendering the system unbootable. It points to a problem right at the start.
But if it does find a volume boot record, what happens then? How does it determine if it's legitimate before trusting it?
Good question. If a volume boot record is found in that critical sector, that small program is loaded directly into a designated memory location. But before it's executed, it undergoes an immediate integrity check, a validation. A key part of this validation is checking the last 2 bytes of this program. They must be the specific hexadecimal value HV5AA.
Ah, the magic number.
Exactly, the magic number. This signature is a fundamental marker universally recognized as indicating a valid boot sector. If that H55AA check passes, then the program is executed. It's important to remember just how small this boot program is. It's a marvel of efficiency. It has to fit entirely within a single 5 and 12 byte sector, and the actual executable boot program itself is only 444 bytes long, leaving just a few precious bytes for the partition table that follows it. This small size means every single byte is critical.
You mentioned the master boot record, the MBR. Can you define what exactly that is? Maybe give us a clearer, more forensic-focused picture of its structure, especially its layout. How is it put together?
Certainly. The master boot record, or MBR, is really a cornerstone of traditional disk partitioning. You have to understand it. It is universally defined as the very first 512 bytes, that's sector 0, of any bootable storage device, like a hard disk or an SSD. This tiny but incredibly mighty sector holds foundational information. It's crucial for the operating system to even begin loading. Its layout is extremely precise and really non-negotiable for a functioning bootable disk, which means any deviation is a huge red flag for an investigator. Okay, let's break down its structure. Think of it like figure 5.1 in the study guide material. The first 444 bytes are allocated for the actual boot program code. This is the executable set of instructions that the BIOS hands control over to. Its job is then to find and load the operating system's own bootloader. Following that, there are 2 null bytes, represented as hex 000000. They just act as an end-of-code marker. Immediately after those nulls, you have 4 16-byte entries. These make up the master partition records. Each of these entries describes one primary partition on the disk. There can be up to 4. And finally, the MBR concludes with that 2-byte hexadecimal value we mentioned, H55AA.
The signature again?
The signature again, the end of MBR marker. It's a critical signature confirming the MBR's validity and integrity. This precise byte-for-byte structure is what an investigator lives and breathes when they're examining a potentially compromised system's disk.
Okay, so those 4 16-byte entries, that's the master partition table. Basically, the disk's internal map or directory. What kind of detailed information is stored within each of those entries, and why are those specific details so important?
Yeah, each of those up to 4 16-byte entries in the master partition table is absolutely critical. It precisely describes a primary partition on the disk. They follow a very specific structure, like you see detailed in table 5.1 from the source material. Understanding each field is paramount for a forensic investigator. Let's break it down. First, at byte offset 0, there's 1 byte, the boot indicator byte. This single byte is incredibly important. A value of H80, hex 80, means the partition is active or bootable. It signifies that this is the partition containing the OS the system should try to load. A value of H00, hex 00, means it's non-bootable. An investigator immediately checks this byte. Which partition was intended to boot? Did a malicious actor change the active partition maybe to hide something or boot something else? Next, byte offset 1 3 bytes. This is the cylinder head sector, CHS, address of the partition start. It's an older addressing scheme, defining the physical location where the partition begins. Still there for compatibility. Then, byte offset 4, 1 byte. The partition type. This byte is a critical identifier. It indicates the type of file system or OS associated with that partition. For example, 800 is no partition, 801 is DOS, 12-bit FAT, 807 is often OS2 or NTFS, 808 is AIX, 8GB is FAT32, HFF might be a Unix bad block table or an extended partition. Different OEs use different values, and some malware might use obscure custom types to hide partitions. Sneaky.
Very. An investigator cross-references this value with known codes to identify legitimate partitions and flag anything suspicious or unrecognized. Byte offset 573 bytes. The CHS address of the partition end, similar to the start address, defines the physical end location. Byte offset 811, 4 bytes, the relative sector offset of the partition. This is the number of sectors from the absolute beginning of the disk, sector 0, to the beginning of this specific partition. This is often called the LBA start sector, logical block addressing. It's vital for precisely locating the partition start, especially if the CHS values are off. And finally, byte offset 1215, 4 bytes. The partition size in sectors defines the total size of the partition. An investigator uses this to calculate the size and make sure it aligns with what's expected, looking for discrepancies. Each of these values can vary, of course, depending on the setup. Their accuracy is paramount for the OS to correctly access the data.
Wow, okay. So that tiny 512-byte section is basically the entire operating system's critical address book, packed with super detailed information about where everything important lives. It's like the system's ultimate minimalist packed suitcase for its journey to waking up. That's incredible efficiency. Now, if we connect this to the bigger picture, why is knowing this MBR layout so incredibly critical for a forensic investigator? You hinted at it. But this sounds like a massive security hot zone.
You've absolutely hit on why this is so critical, and this raises a truly paramount question for forensics, because the MBR is, without exaggeration, a prime target for malware, specifically for sophisticated bootkits. These are designed to load malicious code before the operating system even starts, making them notoriously difficult to detect by traditional antivirus software. Think about it. If a bootkit compromises those first 444 bytes of boot program code, it can redirect the system startup flow to its own malicious payload, granting it stealthy, persistent control long before any security software loads. An investigator wouldn't just be looking for that H5AA end marker. No, they'd be meticulously comparing the entire 512-byte MBR byte for byte against a known good MBR signature for that system type. Any deviation, even a single altered byte in the boot code, or the absence or alteration of that H5AA marker, is an immediate, unmistakable sign of MBR corruption or intentional tampering.
So even one byte off is a huge red flag.
A huge red flag. A malicious bootkit might subtly alter the boot code before this marker, or even spoof the marker itself, which is why a bit-for-bit comparison is one of the very first things they do. We can also use this knowledge to recover lost partitions if the partition table gets accidentally overwritten or corrupted somehow. By reconstructing those 16-byte partition entries, an investigator can often recover access to seemingly lost data. This ability to spot a tampered MBR or to meticulously reconstruct a damaged one is truly where an investigator earns their stripes. It's often the first and most fundamental line of defense an attacker tries to breach. And, speaking of recovery and repair, it's worth remembering that old-school command, FDISK MBR. While definitely not a forensic acquisition tool itself, it's a powerful example. Refreshing the MBR, essentially writing a clean default MBR over the existing one, can overwrite malicious code that might have taken root there, assuming you're starting with a clean FDISK utility, of course. It just highlights how vulnerable, yet critical, this initial sector is. This is where it gets really interesting for finding those hidden traces that malicious actors try to conceal by embedding them deep in the boot process.
That's powerful insight for an investigator, truly making that tiny MBR a huge area of focus. Okay, now that we understand the universal boot process up to the MBR, let's pivot to how different operating systems take over and load themselves into memory after the MBR points them in the right direction. Let's start with a foundational classic, MSDOS. Its boot process might seem, well, quaint today, but it laid crucial groundwork, didn't it?
Let's absolutely start with MS-DOS. Yeah, its boot process might appear elegantly simple by today's standards, almost like a children's book compared to modern OCs. But it lays the foundational groundwork for understanding more complex systems, and many of its principles still resonate today. Okay, so once the volume boot record program has done its job finding the boot sector, verifying its integrity with that H55AA marker, it only has a couple things left to do for MS-DOS. It looks for the existence of two key system files, io.sys and msdos.sys. Or maybe IBM-DOS.com and some older IBM versions. And then crucially, it loads and executes io.sys. Once ISIS is successfully running, that initial boot record program, its job is done, it's no longer needed, and control is fully handed over. Now, IOSys contains a routine called sysint, which stands for System Initializer. This sysint routine is a crucial facilitator. It's responsible for loading additional drivers and settings the system needs to finish loading the OS. As part of this sysint process, it then loads the MS-DOS program. MS-DOS then takes over the primary functions, resetting the disk system, resetting and initializing any other attached devices that weren't handled by POSD, and setting the system to its default parameters, basically preparing the basic environment.
Okay, so io.sys and MS-DOS get the core system up and running, defining the bare-bones operating environment. What about user customization or loading specific hardware drivers? How was that handled back in the DOS days?
Right, good question. For customization and handling special hardware, the sysint routine then checks for another special configuration file named config.sys. It looks for it in the root directory of the default boot device. If config.sys is found, its contents are meticulously parsed and passed over to MS-DOS for processing. This file contains critical directives that allowed users to customize system settings, like the number of files and file buffers to allocate, which directly impacted performance back then. And crucially, it also contained commands to load additional device drivers for special attached hardware devices, custom sound cards, CD-ROM drives, network cards, things like that. It's how the system got tailored to specific hardware and user preferences. A truly fundamental form of customization that we often just take for granted today.
Yeah, we just plug things in now.
Pretty much. For an investigator, finding and analyzing an old configus can be like opening a time capsule. It can reveal the exact configuration of a system at the time, which drivers were loaded, and even point to unusual or custom hardware that might be relevant to an investigation. After configus is processed, the Scicent routine loads command.com. This is often referred to as the shell program. It's essentially the primary user interface for DOS, the gateway for interaction. It contains the last of the device extensions to the base OS, and it also houses all the standard built-in command line programs users interact with directly: echo, dir, format, etc. The very last thing command.com instructs Scicent to do is look for another special batch file in the root directory, autoxcc.bat. This is a user-defined batch file. It might contain programs and commands the user wants executed automatically every time the system starts up. Could be anything from setting environment variables like the path to launching a specific application or game menu. If autoxcc.bat is found, command.com executes all the directives within it sequentially, top-down. Once that's complete, the user is finally presented with the familiar command prompt, typically showing the default drive letter, a colon, and the greater than sign like A. And interestingly, even that prompt could be customized by the prompt command within autoexec.bat itself.
So it's a very sequential, almost scripting-like process then, defining the entire environment for the user, from core system settings right down to the initial commands they might want to run. It's a clear, step-by-step assembly of the operating environment, like building a house brick by brick, in order.
Exactly. A very transparent, almost linear progression. Makes it relatively straightforward to trace, actually. Now let's move forward a bit in time to Windows XP. Here, the boot process gets significantly more sophisticated. It moves from that simple scripting model to a more robust, multi-stage loading process. And there's a key player called NTLDR involved. On disks configured to boot Windows XP, after the MBR and partition table have done their work, the volume boot record program looks for a program called NTLoader, or NTLDR for short. This program immediately takes on its first critical task, figuring out the file system of the default boot drive, which would typically be either the older FAT file allocation table or the more advanced NTFS, NT file system. This determination is crucial because how NTLDR interacts with the disk, how it reads files, how it handles permissions, depends entirely on which file system is in use.
Okay, and what if the computer wasn't shut down properly, or maybe it was put into a sleep state like hibernation? How does NTLDR handle that difference between a fresh start and resuming a previous session?
That's a great point, and it really showcases the added complexity of modern operating systems compared to DOS. If the operating system had been put to sleep or placed in hibernate mode, that state where the entire contents of RAM are saved to disk, NTLDR is specifically designed to detect the situation. It does so by looking for a special file called hyberfill.sys in the root directory. If hyberfill.sys is found, it means the entire system state was saved to disk before power was cut. In this scenario, NTLDR will then reload the entire contents of that hyberfill.sys file directly back into RAM, effectively resuming operations at the exact point the system went to sleep, allows for a very quick return to the previous session, preserving open apps and documents.
Very convenient.
Very. Now, for an investigator, the presence and integrity of hyberfill during sys can be absolutely critical. It contains a snapshot of the system's RAM at the time of hibernation. It could potentially hold volatile evidence like running processes, network connections, encryption keys that would otherwise be lost during a cold shutdown. Analyzing it is often key. However, if hyberfill during sys isn't present, indicating a fresh boot or a proper shutdown. NTLDR then searches for the boot.ini file, which is also located in the root directory of the default boot drive. This file is crucial for presenting boot options to the user. NTLDR will display the versions of the operating system configured in boot.ini, this is the boot menu. It then waits for a specified number of seconds for the user to make a selection before automatically loading the first or default option in the list. This menu is what you might remember seeing if you had, say, multiple Windows XP installations or maybe a recovery console option. It's possible to manually edit boot.ini, yeah, but like our source material mentions, you have to be careful. Just removing lines without using the proper OS tools can lead to issues, as the OS might still technically exist on disk, creating a mismatch. From a forensic perspective, boot.ini is a key file to examine closely. Any unauthorized modifications, maybe the addition of a suspicious boot entry or altering default boot parameters like no execute opt-in, could indicate a bootkit or an attempt to launch a hidden OS or malware payload.
Right, so boot.ini gives the user choices and determines the initial boot path. Once an OS is selected from that menu, what's the next step in verifying the system's readiness and actually bringing the operating system online?
Okay, so after an OS version has been selected from the boot menu, either by the user or just the default timing out, NTLDR proceeds to run the ntdttet.com program. This program has a very specific and critical role. It's responsible for systematically gathering and verifying the configuration of the computer's hardware. It essentially takes a detailed inventory of all the detected hardware components, CPUs, memory, bus types, adapter cards, everything. And it ensures they're ready to be handed over to the operating system kernel. For an investigator, unusual behavior or errors reported by ntdtech.com could potentially point to hardware tampering or maybe the presence of stealthy, unexpected devices. Following this hardware verification, two extremely important files are loaded into memory. First, the hardware abstraction layer dynamic link library, HAL.dll, is read into memory.
The HAL, right?
The HAL. This layer provides a consistent interface between all the diverse hardware components in the OS kernel. It allows the OS to interact with different types of hardware in a standardized way without needing to know the specific, messy details of each component. Immediately after HAL.dll, the Windows kernel itself, NTOSKRNL.exe, is loaded. This is the very core of the Windows operating system, responsible for managing all the system's resources. Now, importantly, NTLDR doesn't just hand over control immediately and blindly, no. It only passes control to the kernel after a rigorous series of driver checks and after verifying that nothing significant has changed since the last run or if the system was shut down improperly. This is a critical validation step to maintain system integrity and prevent unexpected behavior. If all these checks pass successfully, the operating system is considered stable, and the end user is finally presented with the familiar Windows XP login screen, prompting for username and password.
Wow, that's a lot more checks and balances and many distinct components involved compared to DOS before you even get to a login screen. So if we connect this to the bigger picture again, why is understanding this Windows XP boot sequence with all these intricate steps so important when investigating a system that might have been compromised?
This raises an absolute fundamental question for an investigator, you're right, because malware, especially those sophisticated rootkits and bootkits, often tries to inject itself very early in this boot process. Why? To achieve persistence and, crucially, avoid detection by security software that loads much later. So knowing about NTLDR, the boot.ini file, ntddtech.com, HAL.dll, ntoskrnl.exe, and these sequential checks helps us pinpoint where and how a malicious program might have gained control or altered the system's startup, possibly even before security software has a chance to load and scan anything. For instance, if boot.ini is modified to load an unfamiliar entry, maybe pointing to a weird file path, or if the NTLDR file itself has been replaced or patched with a malicious version, its file size or hash would be different. These are strong indicators of compromise. An investigator would use forensic tools to examine the integrity of these critical boot files, check their hashes against known good versions from clean installs, and meticulously analyze the boot log, like ntbtlog.txt, for any deviations or errors. The sheer number of checks during this phase, depending on configuration, OS version, admin options, offers many potential points for analysis and detection. Like the source material mentions, even Microsoft's own TechNet articles delve deep into troubleshooting this complex startup. That just underscores its importance as a critical attack surface and, therefore, a critical forensic examination point. It's really about looking for anomalies in that expected choreography of system startup. Anything out of place is worth investigating.
Okay, moving from the structured world of Windows then, let's turn our attention to Linux systems. They have their own robust bootloaders, primarily LILO and the more modern GRU, don't they? Providing a different approach to bringing the Linux kernel online.
They absolutely do, and they really showcase the open source philosophy of choice and flexibility. When a system is configured to load a Linux-based OS, after the MBR points the way, the next program it finds will typically be either the Grand Unified Bootloader, GRUB, or the older Linux loader, LILO. Both are fundamental bootloaders for Linux. LILO is generally the smaller, less feature-rich version. You might find it on older or more minimal Linux installs. GRUB, on the other hand, is definitely the bootloader of choice on most modern Linux distributions. Why? Because it allows for much more interactive choices and flexibility during the boot process. It handles diverse hardware and multiple operating systems, maybe dual booting with Windows with greater ease. Let's break down LILO first, though. LILO is famously known as a two-stage loader. The first stage is extremely small, tiny really, typically stored within those 444 bytes of the master boot record itself. Its main jobs are just to gather crucial disk geometry information and then load the second, more substantial stage of the bootloader. This second stage is then loaded into memory, and it's usually at this point that the Linux version information gets displayed on the screen. Now, if there's more than one Linux kernel available on the system, maybe you have multiple versions installed for testing or recovery, and it's configured in LILO's configuration file, usually boot.b. Then a menu of the available operating system versions is displayed to the user.
Right. So LILO acts as a selector for different Linux kernels, like a simple menu for the system's core. What happens once a choice is made from that menu, or if there's just a default kernel set to load?
Okay, so once either a menu choice is made by the user or the default OS version kernel is selected automatically after a timeout. That specific kernel, along with the contents of the initial RAM disk, or initride, are loaded into RAM. The initride is important. It's a temporary root file system. It contains essential modules and scripts needed to mount the actual root file system later on. At this point, LILO's job is pretty much done, and it gracefully gives control directly to the loaded kernel. Typically, upon completion of the LILO boot process, you're presented with a command line login prompt ready for user interaction. Now, for an investigator, knowing the important files associated with LILO is crucial. You need to know where to look. These include SpinLILO, that's the installer program that actually writes LILO to the MBR boot. That's the bootloader itself, stage 2. Bootmap. This file tells LILO precisely where the kernel is located on the drive, which is critical, and most importantly, at lilo.com. This is the main configuration file for LILO. It dictates the boot options, kernel paths, timeouts, everything. Examining these files, especially lilo.com, can reveal a lot about a system's boot configuration, potential hidden kernels, or even attempts to modify the boot sequence.
And how does GRB, the more modern and widely used choice, differ from LILO in its multi-stage approach? Does it offer more flexibility, as you mentioned?
GRUB, the Grand Unified Bootloader, is indeed far more flexible and robust, much more powerful. It's also technically a multi-stage loader, though it often involves what's called a stage 1.5, which is a key distinction from LILO. Like LILO, GRB starts with stage 1, which is also typically loaded into the 444 bytes of the MBR. However, GRU's stage 1 is more adaptable. It will then load either stage 1.5 or stage 2, depending on the system's configuration and needs. Stage 1.5 is usually found in the boot partition. It's necessary when the boot drive uses logical block addressing, LBA mode, that's the modern way to address sectors, rather than the old cylinder head sector, CHS method. It's also needed if the boot partition happens to be located beyond cylinder 1024, which was a historical limitation for older BIOS systems. Stage 1.5 basically allows GRUB to understand and access more complex file systems like X2, X3, X24 before the main kernel is loaded. Gives it more smarts early on.
Okay, so it bridges that gap.
Exactly. Then, the stage 2 bootloader is read into memory. This stage is far more sophisticated than LILO's second stage. It's responsible for loading the operating system kernel and the inonated contents into RAM, similar to LILO. However, GRUB's stage 2 is capable of parsing much more complex configuration files. It can automatically detect various operating systems, even non-Linux ones like Windows, and it allows for dynamic selection and even command line editing of boot parameters right at the menu. If multiple OS versions are found in GRUB's configuration file, maybe different Linux distros, or Windows alongside Linux GRUB displays a comprehensive menu. It waits for a user choice before loading the configured version. This menu often provides more options too, like recovery modes, older kernels, memory tests, stuff like that. Once a selection is made, GRUB gives control of the system to the kernel, and the end user is presented with a login prompt, which could be either a command line or a full graphical user interface, GUI, depending on how the system is set up.
And given the vast number of Linux distributions out there, where would an investigator typically find GRUB's configuration files? Is there a standard location, or does it vary a lot?
That's an excellent point about the variety in the Linux world. Yeah, the GRUB configuration file can indeed be in several locations and might even have different names depending on the specific version of GRUB or the distribution of Linux. Common locations include bootgrubmenu.lst. This is typically used by distributions like SUOC and Debian, or older Ubuntu versions. Fedora, Red Hat, CentOS, and newer Ubuntu versions often use bootgrubgrub.conf or bootgrub2grub.cfg for GRUB2. Sometimes grub.conf might just be a symbolic link to menu.lsd or grub.cfg for compatibility.
So you need to check a few places.
You do. For an investigator, systematically checking these common paths is critical. What's also particularly interesting from a forensic standpoint is that the GRUB configuration file isn't always on the main hard drive. It can even be located on a removable USB drive, or loaded from a network share using PXE boot, which can be both a convenience for legitimate users, maybe for rescue systems, but also a significant forensic challenge if an attacker is using a custom hidden boot configuration stored elsewhere.
Okay, so GRUB definitely gives more interactive choices and greater flexibility, making it the preferred modern loader for its adaptability across different scenarios. For an investigator, what's the key takeaway about these Linux bootloaders, both LILO and GRUB? What should they be most mindful of in terms of potential compromise or finding vital clues?
Yeah, what's absolutely fascinating here, I think, is how both LILO and especially GRU manage multiple kernels and boot options. They provide a very flexible but also complex and therefore potentially vulnerable startup environment. For forensics, analyzing their configuration files at clio.conf for LILO, or GRUB's various menu.lst, grub.conf, or grub.cfg files can reveal absolutely crucial information. These files might show attempts to boot into alternative, potentially malicious kernels that an attacker has sneakily installed to maintain persistence.
Ah, like a hidden backdoor kernel.
Exactly. Or they might even be used to hide an entire operating system from plain view by not including it in the main boot menu. An attacker could configure the system to boot a compromised kernel by default, maybe one that looks legitimate but has keylogging or remote access built in. Or an investigator might find entries for hidden recovery partitions that an unauthorized user created for later access. Knowing these multi-stage processes and the specific files involved helps us understand the intent behind a system setup. It helps us detect any unauthorized modifications to the boot sequence. This is a primary area for detecting Linux rootkits or other low-level compromises, as they frequently target the bootloader to gain that early control over the system before security modules load. It's really about understanding the system's true roadmap to life, which might include secret detours an attacker has paved.
Okay, really good insights there. Now let's switch gears entirely. Let's move from the open source world over to Apple's Macintosh, specifically macOS on Intel-based processors. It has its own unique startup sequence using something called open firmware and EFI, which I imagine comes with its own distinct set of forensic considerations.
Indeed, Apple definitely carved its own path here. While we've been talking about traditional BIOS, macOS X, or MacOS as it's now known, on Intel-based processors leverages its own distinct firmware environment. This is known as open firmware, which is based on the IE 1275 standard. Now, it functions very similarly to BIOS in its overall purpose, managing initial hardware setup and booting the OS, but it's fundamentally different in its implementation and capabilities. It offers more programmability, for instance. Just like any other computer, when you hit the power switch on a Macintosh, the system goes through a power on self-test, a post, it resets the microprocessor, and then it begins executing its initialization code. But in this case, it's open firmware rather than BIOS. This extensible firmware interface, or EFI, which is now the standard replacing BIOS on most modern PCs too, by the way, much like the BIOS, checks the machine's configuration. It loads any device ROMs it finds into memory, and then it searches for a default boot device based on settings. And here's where it gets really interesting for user control and, by extension, for forensic examination with what Apple calls snag keys.
Snag keys. That sounds intriguing. What exactly are those, and how do they impact the boot process, particularly for someone like an investigator needing to interact with the system before the OS fully loads?
The snag keys are a fantastic, really powerful feature of the Macintosh boot process. They offer numerous optional startup functions based on user input right at the moment of power-up. These are usually single keys or maybe specific key combinations that, when you hold them down during startup, can force the system to boot from specific devices or enter special modes. This is incredibly useful for troubleshooting, system maintenance, or from a forensic perspective, gaining access to a system in a controlled manner without fully loading the potentially compromised operating system. It gives you options. For example, pressing and holding the C key during startup will attempt to force the Mac to boot from an optical CD-DVD-ROM drive.
Ah, perfect for a forensic boot disk.
Exactly. Invaluable for an investigator who wants to boot from a forensic live CD or maybe a recovery disk. Pressing and holding the DT will attempt to boot from the first internal hard disk drive, bypassing any other boot order settings. The N key is used to attempt to boot from the network interface controller. Could be important for network-based OS installs, recoveries, or maybe loading a network-based forensic tool. And, though much less common today, pressing the Z key would historically attempt to boot from an external ZIP drive, if you can believe it.
Wow, a ZIP drive, blast from the past.
Right. Beyond these specific boot device selections, it's also possible to enter the EFI interactive console mode. You do this by pressing and holding the Command-Option-OF key combination during power-up. This gives you a powerful, low-level command line interface before the OS even loads, allows for direct interaction with the firmware. If you happen to try this out and then want to proceed with booting the operating system normally, just typing Mac boot at the prompt will let the Macintosh finish its startup sequence. For those interested in digging deeper into these capabilities, there's an excellent mirror of the Open Firmware Working Group available online with command references and more detail. For an investigator, these snag keys and the EFI console are absolute superpowers. They offer direct control over the boot process to potentially bypass passwords, boot from trusted media, or perform early diagnostics without interference.
That's an astonishing level of control right at the initial startup. Truly like having a secret handshake or a backdoor into the system's early decision-making process. Yeah. So what's the next step after Open Firmware and EFI decide where to boot from, which options like snag keys to use?
Okay, so once the boot device and any options are determined, the EFI program located in the boot.efi file takes over. This boot.efi is the crucial piece of the boot loading process that's responsible for loading the actual macOS kernel and initiating the user interface. It effectively bridges that gap from the low-level firmware environment to the fully functional operating system we recognize. This is a significant transition where the system starts building its user-facing personality. Now, it's interesting, for many die-hard Macintosh users who grew up with the classic macOS, the initial move to OS X wasn't immediately seen as a move to an open-source Unix environment. It felt very different. But it wasn't long before they realized their beloved Mac was now, at its core, a really robust Unix machine underneath that Aqua interface. When you look at the roots of macOS, or OS X as it was, a large number of its open-source modules and programs were obtained from various highly respected groups and projects across the computing world. Places like Carnegie Mellon, FreeBSD, the GNU Project, the Mach Microkernel Project, X386 for graphics, and NextStep and OpenStep, which Steve Jobs brought back to Apple. This rich lineage gives macOS a powerful and remarkably stable foundation.
So macOS, which presents as this very polished, intuitive, and user-friendly system, has this deep, powerful Unix foundation hidden underneath, almost like a carefully engineered, high-performance engine beneath a beautiful chassis. What's the actual name of the macOS kernel, and what are its key components that make up this hybrid engine?
That's a great analogy. The elegant facade hiding a robust engine. Perfect. The actual macOS kernel name on the boot drive is XNU. It's not what you'd call a monolithic kernel, but rather a hybrid. It's comprised of several distinct modules that work together seamlessly to provide the complete operating system experience. Understanding these components is key to understanding macOS's architecture. First, there's Mach. This is a microkernel that provides the fundamental service layer to the larger XNU kernel. It handles core OS tasks like process management, memory protection, and crucial inter-process communication, IPC. It's the low-level workhorse. Then you have the BSD components. That's Berkeley Software Distribution. These provide the primary system program interface, the APIs. They offer familiar Unix APIs and services, giving macOS its powerful command line capabilities and POSIX compliance. Vital for developers and absolutely for investigators using standard Unix tools. The I/O kit, often called I/O toolkit in older docs. This provides essential driver support. It allows the kernel to efficiently interact with a vast array of hardware devices, from graphics cards to network interfaces to USB ports. Now, for an investigator, this is where malicious device drivers or hardware-level intercepts might try to hide. Within the I/O kit framework, libsa and libkern. These are vital kernel libraries. They offer common functions and routines that the other kernel components can call upon, ensuring efficiency and consistency across the board. The platform expert. This acts as a motherboard-specific hardware abstraction layer, similar in concept to the HAL in Windows, but tailored for Mac hardware. Its role is to ensure compatibility and smooth operation across different Mac hardware revisions, translating generic kernel commands into specific hardware instructions. And finally, Apple I/O components. These provide the unique Mac interfaces and integration points, managing Apple's proprietary hardware and peripherals, things like Thunderbolt, specific display protocols, etc. While these open-source elements form the backbone, Apple uses many proprietary components on top to invoke that distinctive Macintosh look and feel we all recognize. Things like Carbon, an older API set, Cocoa, the modern object-oriented API, Quartz, the 2D graphics rendering engine, OpenGL, and now Metal for 3D graphics, QuickTime for multimedia, and especially the Aqua interfaces, those iconic graphical user interface elements like the dock, menus, windows. These are just a few of the unique closed-source elements that make the Macintosh so special and give it its recognizable, polished user experience.
The snag keys you mentioned offer fascinating ways to control the boot, truly giving users and investigators a lot of power even before the OS loads. almost like a secret handshake with the hardware. So, if we connect this back to the bigger picture, why are these Mac-specific boot details so important for an investigator who might encounter a Mac system out in the field?
Yeah, this raises an absolutely important question for any forensic investigator working today. Because the ability to use those snag keys or to enter the EFI console means we have incredibly powerful methods to influence a Mac's boot before it fully loads the operating system. This could be absolutely crucial for bypassing a lock operating system password, for example. Or, more commonly in forensics, booting from a trusted forensic disk image, maybe on a USB drive or CD, to preserve volatile evidence on the internal drive. Or even just performing a clean boot for diagnostic purposes without interference from potential malware loaded by the installed OS.
Right, like using the C key to boot off your forensic toolkit.
Exactly. An investigator could use the C key to boot a forensic Linux distribution from a CD or USB, acquire a forensically sound image of the Mac's internal drive, and then analyze that image safely without ever touching or altering the potentially compromised macOS environment on the target machine. And understanding macOS's Unix-based XNU kernel and its components' MacBSD I/O kit helps us predict exactly where system-level changes or even sophisticated rootkits designed specifically for macOS might try to hide. For instance, knowing that specific driver components live within the I/O kit framework means an investigator would target that area when looking for malicious driver injection, checking for unsigned drivers or unusual load order, or drivers communicating over unexpected network ports. It also reminds us of that unique Macintosh file characteristic. Files often have two forks, a data fork, where the main data usually is, and a resource fork, which can hold metadata, icons, code snippets, or sometimes hidden data.
Oh, yeah, the forks.
Right. That's highly relevant to file analysis, and something an investigator needs to be acutely aware of when examining individual files for hidden data or attributes that wouldn't exist on a Windows or Linux file system. This deep architectural knowledge really informs where and how to search for anomalies effectively on a Mac.
And just to clarify something that comes up a lot, with Mac OS X, now Mac OS running on Intel-based systems for quite some time now, can it legitimately run on a standard non-Apple PC? It's a question I'm sure many curious users and perhaps even some investigators doing research have wondered about.
Yeah, that's a very common question. It has generated a lot of discussion and activity, especially in online communities, ever since Apple made that big transition to Intel processors back in the mid-2000s. While there's been a lot of talk on various hacker sites and forums about hacked versions of macOS, often referred to as Macintoshes, running on regular Intel-based PC hardware, it's crucial, absolutely crucial, to understand that officially using modified macOS versions on non-Apple hardware is a direct violation of Apple's strict end-user licensing agreements. EUA.
So legally, it's a no-go.
Legally, it's a no-go. So while it might be technically feasible to some extent, often requiring significant effort, custom bootloaders, patched kernels, and specific compatible hardware, it's not a legitimate, legally sanctioned, or supported way to run the operating system. From a forensic standpoint, encountering a Macintosh system during an investigation could actually be a significant red flag in itself. It often implies unauthorized system modifications, potentially done to circumvent security features or licensing restrictions. And it could also introduce instability or unknown variables into the system's operation, making analysis trickier. You don't have a known baseline.
That's a very clear and important distinction to make, both legally and forensically. Okay. Now, with the increasing prevalence of Macs in homes, businesses, and even in some traditionally Windows-dominated environments like labs or creative studios, forensic tools specifically designed for macOS have become absolutely essential for investigators, haven't they? What are some of these specialized tools that professionals rely on to uncover digital evidence on Mac systems?
You're absolutely right. It's true that only relatively recently has the Macintosh begun to be more widely accepted and integrated into the broader corporate and forensic community. It used to be more niche. With this increased adoption, the availability of specialized forensic tools for macOS has become not just beneficial, but truly critical. It's crucial that an examiner not only has access to these tools, but also has a solid understanding of how they work, what their limitations are, and, most importantly, can prove their findings by demonstration and clear explanation in a court of law. That concept of forensic soundness, ensuring evidence is acquired and analyzed without any alteration, is paramount, regardless of the OS. One of the leading and most comprehensive providers of forensic software specifically for the Macintosh platform for a long time has been BlackBag Technologies, Inc. The Macintosh Forensic Suite is, or was, an incredibly powerful collection. The source mentions 26 distinct modules. These could be launched individually for specific tasks or conveniently accessed and managed through their integrated Forensic Suite toolbar. Note, BlackBag was acquired, but the tools and concepts remain relevant.
26 modules. That sounds incredibly comprehensive for a single suite. Can you highlight some of the key tools within that BlackBag Forensic Suite and explain their particular value for an investigator dealing with a Mac?
Absolutely. Let's look at a few of the standout utilities described in the material, understanding their specific forensic applications. First, directory scan. This tool is like an investigator's window into the entire Mac file system. It lets you view all files and folders on a Macintosh volume. And when I say all, I mean all, including invisible files, system files, hidden directories, and files across any mounted storage device, whether it's internal, USB, FireWire, whatever. For each file, you can examine crucial details. Data fork and resource fork data sizes, remember that unique Mac thing that can hide data.
Yep, the forks again.
Yep. Also, creator and type codes, which can identify the originating application even if the extension is changed. And critically for forensics, all the date timestamps, creation, modification, last access, metadata change times. You can then select individual files or folders for export and generate comprehensive reports for documentation. For an investigator, this provides an unparalleled overview. It allows them to spot hidden or unusual files that a standard user or even standard OS tools wouldn't see. Could be malware payloads, exfiltrated data, hidden logs. Next, FileSpy. When you need to quickly look inside a specific file that might have forks or unusual structures, FileSpy is excellent. This utility lets you view either the data fork or the resource fork within a file, see their relative sizes, and even navigate directly to any sector within the file. It includes an ASCII filter, which is incredibly useful for examining raw data, like viewing XIF data embedded in a JPG file to find camera metadata, GPS coordinates maybe, or reading plain text hidden within application resources or Slack space. This granular access is vital for uncovering data hidden within a file structure, a common tactic for concealing information. Then there's HeaderBuilder. Macintosh file headers, especially older classic ones, can be complex and calculated structures. Manually changing or repairing them with the generic X editor can be incredibly time-consuming and really prone to mathematical errors, messing up the file. HeaderBuilder simplifies this significantly. It allows you to make changes to headers easily, maybe to fix corruption or reassociate a file type, and then it immediately generates the CRC32 checksum and the MD5 hash of the modified file.
So it helps maintain the integrity trail.
Precisely. This is crucial for maintaining and verifying data integrity. If a file header needs correction for analysis, HeaderBuilder lets an investigator make the change and immediately document the new cryptographic hash, proving exactly what was changed and the new state of the file. That's vital for courtroom presentation. Beyond these, the suite described contains numerous other specialized utilities, each with its own forensic use. Breakup for splitting large files, Comment Hunter for finding keywords and file comments, DCFLD Desistant for Mac native forensic imaging using DCFLDD, File Searcher for advanced file name or type creator code searches, Graphic View for media viewing, HFS Extractor for image format conversion, Image Buster for keyword searching inside image files, List Builder for custom keyword lists, Lockmaster for file locking unlocking, McCarver for carving deleted files from free space, Phantom Search for finding invisible files, Typer for viewing changing type creator codes, and Volume Explorer for deep HFS plus partition analysis. It's a very complete toolkit described there.
That is an impressive, truly exhaustive suite of tools for deep analysis. It really sounds like they help an investigator get past the typical user interface, peel back the layers, and see what's truly going on at a much lower level.
Yeah.
Which is exactly what forensic investigation's all about, right?
Indeed, they provide that necessary granularity and specialized access that generic tools or just using the OS itself simply can't offer reliably for forensic purposes. However, it's also critically important to discuss tools that, while powerful and popular among users, are not suitable for forensic imaging or evidence preservation. Take Carbon Copy Cloner, or CCC, for example, a very popular tool.
Right, Carbon Copy Cloner. It's a widely used backup tool for Macs. Countless users rely on it. What's the distinction here? Why is it a no-go for forensic work, as you put it?
Okay, Carbon Copy Cloner, created by Mike Bombich, is undeniably a fantastic utility. It's designed specifically for making backups or copies of important data on your Macintosh. It essentially acts as a user-friendly front end for several less intuitive utilities that are already part of macOS, like rsync or Ditto. As its name implies, CCC can clone one hard disk to another or clone a disk to an image file on another drive when you use its default options. This is fantastic for personal backups, for migrating your system to a new drive, or creating bootable duplicates for everyday use or emergencies. It works really well for that. However, and this is the critical distinction that every investigator must understand, it should be explicitly native that CCC does not make forensic copies of the original media. It's not designed for that.
Okay, so not bit for bit identical.
Exactly. This is a vital point because the legal principle of forensic soundness demands an exact bit-for-bit copy of the entire storage device. No alterations, no omissions, no selection of data. Every single bit matters. CCC, by its very design and purpose as a backup tool, makes conscious decisions about what to copy and what to exclude. For instance, the source notes it only clones Macintosh formatted volumes by default. It doesn't necessarily recognize or clone DOS or Unix formats that might be present on a multi-boot system's drive. And if you look at its advanced settings and documentation, there's a specific list of files and directories that are intentionally not copied during a clone. This can be due to compatibility issues like copying from an old Power PC Mac to an Intel Mac, or simply because they are temporary files, caches, sleep images, trash contents, things that don't typically need to be in a user backup. While the documentation provides more detail on these exclusions, this intentional selectivity, this filtering, fundamentally underscores why it's not forensically sound. It doesn't capture the entire state.
Okay, so it's great for everyday personal backups and convenience, but a definite no-go for courtroom evidence where every single bit counts and must be accounted for. Why is that distinction so profoundly important that an investigator must be aware of it to avoid potentially jeopardizing a case?
Well, if we connect this to the bigger picture of legal admissibility, that legal principle of forensic soundness requires an exact bit-for-bit, unadulterated copy of the original media. This means preserving every single bit of data, including deleted file space, unallocated clusters, file slack space, partition tables, everything. Because any of these areas could hold crucial evidence fragments. CCC, by intentionally excluding certain files or directories, or by not handling all file systems uniformly, or by potentially updating timestamps as it copies, fundamentally doesn't meet that stringent standard. For evidence to be admissible in court, an investigator needs to be able to demonstrate, usually through cryptographic hashing, that the acquired copy is an identical duplicate of the original source media, preserving the entire digital state at the time of acquisition. Because CCC makes selective choices about what it copies, it fails to preserve that complete digital footprint. This could lead to serious questions in court about data integrity, chain of custody, whether evidence was missed or altered. Ultimately, it could jeopardize the admissibility of any evidence derived from that copy. An investigator absolutely needs tools that provide provable, bit-level fidelity, ensuring that what they acquire is an exact, forensically sound replica of the original. Anything less is just too risky professionally and legally.
That's a crucial point for any professional dealing with digital evidence. Integrity is absolutely everything. Okay, finally, sometimes an investigator might be working on a Windows workstation, which is still a very common forensic platform, but they need to examine a Mac-formatted volume. Is there a solution for that kind of cross-platform access in that common scenario?
Absolutely, and that's where a utility like MacDrive comes in incredibly handy. It solves that exact problem. It's important to clarify its nature first. MacDrive, like version 6 or 7 mentioned in the source, though newer versions exist, is technically not Macintosh software. It's a Windows program. What it does is it allows a Windows operating system to natively mount, read, and often write to Macintosh formatted volumes, like HFS+. The source mentions MacDrive 6 for older Windows like 2009 SE and MacDrive 7 for Windows XP Vista Server 2003. Newer versions obviously support Windows 10, 11, etc. This utility is incredibly helpful if you have a Windows-based forensic workstation and you just quickly need to view files on a Mac-formatted drive, maybe from an external drive you received or an image you mounted. It saves you needing a separate Mac machine or dealing with complex virtual environments or firing up a full Mac forensic tool just for simple file browsing or triage. From its main menu, you typically get quick choices like exploring a Macintosh volume, just as if it were a native Windows drive, like E or F. You might also be able to burn a Macintosh formatted CD or DVD, or even format or repair a Mac volume directly from within Windows. It basically teaches Windows how to speak Mac HFS Plus Dutchy. As a nice visual cue for easy identification, any Macintosh volumes mounted through MacDrive are typically shown within Windows Explorer with the distinctive small red Apple logo next to their drive letter. Makes them easy to spot. This cross-platform compatibility is a significant convenience for investigators working in mixed OS environments, which is very common. Okay, so to bring all of that together, let's try and recap the critical insights from our deep dive into these boot processes. We need to ensure we understand not just what happens, but really why it matters so much for a forensic investigator. First key takeaway is understanding the universal boot journey. That systematic progression, right from the very first power good signal bringing the circuits online, through the rigorous power on self-test, PS Bishop, just checking all the hardware, then to the crucial stage of locating the master boot record, MBR, then finding the specific operating system's own bootloader, loading its kernel, and finally presenting a user prompt. This entire sequence is the fundamental life cycle of a computer starting up. For an investigator, knowing the sequence is like having the blueprint of a crime scene. Any deviation, any unexpected step or error is an immediate point of suspicion. Second, MBR mastery is absolutely non-negotiable. Its precise location, cylinder 0, head 0, sector 0, or just sector 0 in LBA. Its fixed 512 byte size, that critical H55A N marker, and the detailed info packed into its partition table entries. These aren't just technical specs, they are the first line of defense and, historically, the most common target for sophisticated bootkits and malware aiming for stealth. An investigator must be able to recognize a legitimate MBR, detect any tampering within its boot code or partition entries, and even understand how to use tools to verify or potentially recover it if possible. Third, the OS-specific nuances are where the systems diverge, and each has its own forensic implications. For MS-DOS, understanding the sequential roles of IOSS, MSDOS, configus, command.com, and autoexec.bat reveals that simple, almost scripting-like boot process. Even old batch files can provide crucial user intent or system configuration details. For Windows XP and similar NT-based systems, the crucial sequence involving NTLDR, hyperphiloceris, potential RAM snapshot, boot.eme, boot options, ntdetect.com, hal.dll, and ntoskrnl.exe shows a more complex multi-stage loading. Each of these files is a potential injection point for malware. Their integrity must be forensically verified. For Linux, the multi-stage operations of LILO and the more modern, flexible GRUB, along with their important config files like etlilo.conf or bootgrubmenu.lsd or grub.cfg, illustrate highly flexible boot processes. An investigator must know how to parse these files to identify legitimate and potentially malicious kernel entries or hidden operating systems. For Macintosh, the role of open firmware and EFI, powerful snack keys for boot options, which are invaluable forensic tools themselves, and the layered architecture of the XNU kernel mock BSD components highlight a distinct and powerful boot environment. Plus, those unique data and resource forks need special forensic attention. And finally, the forensic imperatives. This whole deep dive really underscores the necessity for investigators to understand each step in every boot process to identify anomalies or malicious activity right from the start. It also highlights the specific utility and the critical limitations. Remember, CCC is not forensically sound for acquisition of specialized tools like the BlackBag Forensic Suite for Mac analysis and cross-platform access tools like MacDrive. This foundational understanding is truly the investigator's core toolkit for deconstructing digital events from their very genesis, from the moment power is applied.
That was a truly comprehensive deep dive. Really getting into the brain of a computer at its most vulnerable, yet maybe its most foundational moment. Understanding these intricate boot processes is clearly not just, theoretical knowledge you memorize for a test. It feels like a practical superpower for an investigator, giving them the ability to read the system's autobiography right from the very first page.
Absolutely. Couldn't agree more. It's all about knowing the entire story of how a system comes to life. Because that narrative, that sequence of events, can hold the key to understanding a digital crime scene, detecting hidden malware that operates way below the OS radar, or even recovering critical data that might otherwise be completely overlooked or seem lost. For a computer hacking forensic investigator, this foundational understanding of system startup is absolutely indispensable. It's often where the most critical parts of an investigation truly begin.
Well, thank you so much for guiding us through this essential, incredibly detailed chapter. It's clear how vital this is. And for you, our listener, we really hope this deep dive has given you a robust understanding and maybe sparked further curiosity about the incredible complexity hidden in plain sight every single time you power on a device.
Yeah, keep exploring, keep questioning things. And remember that every startup is a new beginning and potentially a new lead for an investigator. Understanding these foundations is always the first step to dismantling the complex problems you'll face, because oftentimes it's the smallest details right at the very beginning of a system's life that hold the biggest secrets.
Join us next time on AudioCert for another deep dive into the official study guides.